Chapter 5, quote from Karl Popper, "Science may be described as the art of systematic oversimplification, the art of discerning what we may with advantage omit." And that definitely describes Chem 1A. I've mentioned that we lie to you sometimes. It's not really lying, but we are omitting confusing details. So we're leaving some things out, and we're just looking at the stuff that helps us to understand. So this chapter is about solutions and aqueous reactions. So chemical reactions occurring in a solution are very, very common. Often those are dissolved in water. On Monday we did a chemical reaction where the reactants were dissolved in methanol, and the reaction occurred when you heated that solution. So a solution is a homogeneous mixture of two substances. It could be salt and water, it could be sugar and water, any two substances that mix homogeneously. A solution has two parts, the solvent and one or more solutes. The solvent is, there's different ways of describing it that fit in different circumstances. In general, it's the thing that there's more of. So in our experiment where you put 2 grams of zinc and 2 grams of iodine in 25 milliliters of methanol, there's a lot more methanol than there was either of the other substances. And so the methanol is the solvent. The solute is the other parts, the things that are dissolved. They're dissolved in the solvent. And there can be more than one. There often is more than one. And how much solute there is variable. We could add a little bit more zinc or a little less iodine. We can still make a solution. When the solvent is water, it is an aqueous solution. And water is the most common solvent. So because the amount of solute is variable, then we need to describe how much solute there is. So we can describe these solutions qualitatively as dilute or concentrated. So a dilute solution has a small amount of solute. A concentrated solution has a large amount of solute. And we have illustrations. Concentrated, so there are a lot more solute particles in this region than there are in the dilute solution.
So there'd be excess.
Well, excess solute suggests that there's a certain amount that we should have, and here it could be anything. So one way to think about this is concentrated frozen orange juice, right? You buy the little can from the freezer, and it's like, even when you let it thaw out, it's like super, super thick, right? And nobody would eat that straight because it's just like way too much, right? It's too concentrated. So what do? You dump it into a pitcher and you add some water. You dilute it, right? You're adding more solvent. Is there water in that concentrate? Yeah, there is, but there's not very much. So you add more water and you dilute it, and then it tastes good. And if you were to add too much water, then it's not going to taste so good anymore, right? Because it's going to taste watery and weak, right? So that's a solution. It can be concentrated or dilute. Any questions about that? Of course, chemists are a lot more interested in quantitative descriptions, and here we're talking about solution concentration, and the most commonly used method in chemistry is something called molarity. So molarity, as its name suggests, has to do with moles. So molarity can be defined as the amount of solute measured in moles divided by the volume of the entire solution measured in liters. So these units have to be used, moles for amount of solute and liters for amount of solution. Molarity is abbreviated with a capital M. We're collecting quite a lot of M's as abbreviations, and so we need to be careful with that. I see a lot of confusion even among Chem 1B students who've already gone through 1A successfully, still just a little iffy about what that capital M means. Capital M is not the same as mole. They're different. Capital M is moles per liter, and mole is just moles. Yeah. We will learn molality, but thankfully I don't think it's today. I don't remember because I don't know what's coming next in the slides. Makes it more interesting. So it's the moles divided by the volume of the entire solution. So it's abbreviated with a capital M, and then we also have lowercase m, which is meters. And then, as he hinted at, molality, this is super confusing, is a lowercase italicized m. Yeah, how do you do that? Handwriting. That, thankfully, is just a little tiny piece of Chem 1A. But the capital M. I often underline my capital M because, let's just take something out of context. Is that a capital or a lowercase m? It's hard to tell. It's lowercase? No, it isn't. It's capital. I was going to make you wrong whatever you said. So you can make your capital M very pointy, and that helps, but I'm usually too lazy to do that. So this is a capital M, and this is a lowercase m. Just so you know what I'm doing. We want to distinguish. We want to distinguish between capital M, which is molarity, and lowercase m, which is usually meters. It can be molality. In front of another unit, it can be milli. Yeah, so many m's. So here's a description of how we would make a solution with a particular concentration. And we're going to be doing this very, very similarly when we do experiment 5B. We're going to make a sodium chloride solution. So here, if we want to make a 1 molar solution, 1 molar has nothing to do with teeth. Molar is 1 mole per liter. The molarity is 1 mole per liter. So instead of, well, just to make it more confusing, we throw another word in there. Anyway, we're going to use a volumetric flask. The volumetric flask has a very long, skinny neck, so that as you fill it to the last little bit, just 1 drop will cause a noticeable rise. And so we can get a much more precise measurement. This is designed to contain a certain amount of liquid. So this is a 1 liter flask, and if we want to make a 1 molar solution, 1.00 moles of sodium chloride per liter, then we need 1 mole of sodium chloride in 1 liter of solution. So we can't measure a mole, we have to measure the mass. So here's the molar mass gives us 58.44 grams of sodium chloride is 1 mole. So we would measure out 58.44 grams of sodium chloride and then transfer it into the flask. That can be a little tricky because the flask is narrow and pouring a solid into a tiny little opening can be hard. Funnels can be helpful there. Then we use DI water and partially fill the flask. We don't want to fill it all the way up because once we get the liquid up into this neck, it's really hard to mix. If we fill it so it's still down here, we can just kind of shake it and get it to dissolve. And so we want to make sure that all the sodium chloride dissolves. And then we will carefully add more water until the bottom of the meniscus is at the line that's etched on the neck of that flask. Then some of these have a cap, some have a stopper. It's got something that will cover the opening, and then we have to mix it thoroughly, and the only way to mix it is to invert it and wait for the bubble to go up and then turn it over again, like 10, 20 times.
Moles can be in relation to grams or liters.
So moles can be in relation to grams or liters. Okay, so I think what you're saying is we have these two different things. This is grams per mole, and then this is moles per liter. Well, this gives us the relationship between the number of moles and the mass of the compound. This gives us the relationship between the number of moles and the volume of the solution that it is in. The liters is the volume of the entire solution, which is the sodium chloride and the water. This is true for pure sodium chloride. This is for a solution, a mixture of sodium chloride and water. This concentration will be different depending on the specific solution. You can make lots and lots of different concentrations. The molar mass of sodium chloride is always the same. And please, please ask questions, even if you think they're stupid, because this concept of molarity is super important. And a lot of students manage to muddle their way through, never just quite getting what it's all about. It's a description of how much of the substance of interest is dissolved in a particular amount. In some ways, it's like a percentage, but the units are special. Instead of grams of solute per liter of solution, which we could do, we can say, well, this solution has 58.44 grams of sodium chloride per liter of solution. And that is also a measure of concentration, but it's not one that's very useful in chemistry. In chemistry, because we're always doing moles in the middle, right? When we use molarity, we can measure the volume of a solution and use the molarity to find out how many moles of solute are in there. And so then we don't actually have to use the molar mass at all. So how many moles of solute are needed to make 3 liters of a 2.0 molar solution? So anytime you see this capital M, that's 2.0 moles per liter. So if I have 3 liters, how many moles do I have? Each liter has 2 moles. If I have 3 liters, 6 moles, right? So I need 6 moles of solute. So here's 3 1 liter beakers. And each of these is 1 liter. And this concentration, 2 moles per liter, tells me that I have 2.0 moles of whatever the solute is in this 1 liter of solution. And in this 1 liter of solution, I also have 2.0 moles. And in this liter, I also have 2.0 moles. So if I want 3 liters of solution, then I need 2 plus 2 plus 2, 6 moles of solute in the 3 liters. Does that make sense? Yes, we can absolutely work that out as dimensional analysis. In fact, molarity is a great conversion factor. I didn't pay her to ask that.
You said it's 2 moles, and that's the big M, but I thought we said that the big M was molarity.
The big M is molarity, moles per liter.
Because if I saw that, I would have thought that that meant molarity.
This,
The big M.
the big M is molarity.
Yeah,
And this is the same.
Molarity and moles are the same.
Molarity and moles per liter. Yeah. So capital M is the same as moles per liter, which is different than just moles.
They learned that in 3A.
You should have learned it in 3A, yeah. But like I said, I've got students in 1B who, some of them did very well in Chem 1A, and they come into 1B and I talk about a 2 molar solution and they're like, they think it's moles, and then they just like totally screw it up. So this is a thing that students often will muddle through but not actually understand. In some of the stuff, like combustion analysis, yeah, muddle through, not a big deal. This is a big deal. Molarity is a big, big deal. So the capital M means exactly the same thing as moles per liter. It's an abbreviation. But moles per liter is not the same as moles. Because moles per liter describes a concentration, and moles just describes an amount. A little bit like the difference between mass and density. Density is a relationship between the mass and the volume of something. Mass is just how much there is. Any other questions about this? Yeah.
Are we ever going to have to determine the full concentration of a given solution?
The what concentration?
Like the full, how concentrated is the solution with given? Okay.
Oh yeah. We're going to do all sorts of concentration calculations. Okay, so this is asking us to calculate the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. So molarity is a bit like density. Molarity is moles divided by liters. And so if we're calculating the molarity, then we use the equation. Molarity, M, is moles of solute divided by liters of solution. And that is something you need to memorize. So if we want the molarity of this solution, we need to know how many moles of solute there are in how many liters, and then we divide and get an answer. Do we know how many moles of solute there are? No, they gave us a mass. We can figure it out, but we have to do a separate calculation. Did they give us the liters of solution? They did. So let's fill that part in at least. So 2.50 liters of solution. And now I need to figure out how many moles of sodium nitrate do we have. Well, we've got 45.4 grams of sodium nitrate. Can we convert grams to moles? Yeah, we can. So we'll multiply by moles and divide by grams. And the conversion factor we need here is the molar mass, the mass of 1 mole. So sodium is 22.99, and nitrogen is 14.01, and 3 oxygens . 85. It's like when you go to the grocery store and it comes out to be $100. Exactly. I could do that if I tried. Does this only have 2 significant figures? Well, as I wrote it, it does, but what should it have? It should have 4, because this has 4, and this has 4, and this has 4. So how do I give that 4 significant figures? 0.00. It's not an exact number. It's calculated. It's 85.00. And I only point that out because I don't want to stick 85 in here and have that reduce the number of sig figs in my calculation. 45.4 divided by 85. 0.53. 411 moles. I'm starting with 3 sig figs in the mass. My molar mass has 4 sig figs, and so the number of moles should have 3 sig figs. I'm going to use this in a calculation, so I'm not going to round it yet. But that's my number of moles. It's going to go in the numerator. I had to do a calculation to find out how many moles there were. So then I take the numerator and divide by the denominator. And this should have, again, 3 significant figures. And the units do not cancel out. They're just both there. Moles per liter. And then when I round this, I get 0.214 moles per liter. We can write it that way, or we can say 0.214 capital M. Yeah.
So when I read this at first, I thought you have to calculate the moles of water too. So is that not? It's just of the solute.
It's just of the solute. Yeah. So you might wonder, oh, why aren't we interested in how many moles of water there are? The water is sort of just the carrier, right? It's a kind of a container for the solute. And when we mix this with something else, the water is not going to do the reacting, it's the solute.
So any solution, it doesn't have to be water. They say they're adding it to any sort of like liquid.
You can make a solution between 2 gases. The air we're breathing is a solution.
Okay.
The predominant gas is nitrogen, and so that would be considered the solvent. And then there's oxygen and CO2 and argon are the primary solutes in the air. You can have a mixture of solids. So an alloy like brass or pewter, stainless steel, those are solutions of solids. We tend to think of a solution as a liquid, like sugar dissolved in water, salt dissolved in water.
So will we be told, or will it be clear which the solute is?
That's a good question. Are we going to be told which one the solute is, or will it be clear? We intend it to be clear. That doesn't mean that it will be clear, but we intend it to be clear. This one specifically mentions it's being dissolved in water. If there's no mention of what the solvent is, you should just assume that it's water, because that is by far the most common solute. So it's also, water is sometimes called the universal solvent. So that's the most common solvent. And the solute is usually the thing that they're giving you information about. Could you figure out how many moles of water are in this 2.5 liters? You could, but would it be useful for anything? Probably not, which is why we're not focusing on that. But those are good questions. Anybody else? .214 molar. So we can use the molarity as a conversion factor. So we use it just like we use the molar mass. So we've got moles per liter. So we can use, as this example, a 0.5 molar sodium chloride solution. That's 0.5 moles per liter. So 0.5 moles of sodium chloride for every liter of solution. So we can write it like this, 0.5 moles of sodium chloride per liter of solution. We can use that if we have the amount of liters of solution and we want to know the moles of solute. Or we can invert this, and that will allow us to convert from moles of sodium chloride to liters of solution. Because we might need 2 moles of sodium chloride for a particular reaction. And we can use the molarity to figure out, well, what volume of this solution do I need to measure out? When we have a molarity of a solution, then we can measure out quantities of the solute using volumetric glassware, beakers, graduated cylinders, instead of weighing everything. And so it makes things a lot more convenient. So how many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? This is coming down to dimensional analysis again. Over and over and over again. So we're going to pull the numbers out and write them down and then try to make sense of them. So 1.55 liters. It's not a very nice 5. And 0.758 capital M. The capital M doesn't help me when I'm trying to convert units, because it doesn't look like a conversion factor. What's the capital M stand for? Moles per liter. So write moles, moles, easier said than done, moles per liter. That's what the M stands for. It's a little bit like when we had the density and it had a slash, the fraction had a slash, grams per milliliter, and I said, well, that's easier to type out on the computer, but when you write it by hand, make it vertical. Capital M is an easier abbreviation, and so we use it a lot, but it doesn't help us when we're trying to convert units. So here, write it as moles per liter. So those are the 2 numbers I was given. And maybe I'm not sure which of those is my starting number, my given unit. But I can figure out what am I asked to find? Grams. So I'm trying to find grams of sucrose. And I'll just use the formula. This concentration per liters of solution, but it's moles of what? Moles of sucrose, right? 0.758 molar sucrose solution. So it's this many moles of sucrose per liter of solution. Sucrose is table sugar, in case you're curious. So I'm trying to find the mass of sugar. I've got these 2 things I could be starting with. This is a per unit. This could be a conversion factor between moles and liters, right? This is just liters. It can't be used to convert anything. So this is the one I'm going to start with, and I'm going to use the other as a conversion factor. And this is almost always how it ends up being. So I'm trying to get from liters to grams.
Just go from liters to moles.
Yeah, I can go from liters to moles because this gives me liters to moles, the relationship between moles and liters. And then how do I get from moles to grams? Molar mass, right? I've got the formula. I can calculate the molar mass. Oh, tedious. Yeah. Life is tedious. Get over it. Any questions about the path? Yeah. Why isn't the 1.55 down here? That's an excellent question. So this is describing the concentration of the solution. The concentration of that solution is the same whether I have 1 liter or 10 liters. This is sugar, so it would be a sweet solution, right? So if you tasted it, it would be sweet. If you had a big vat of it, same concentration, it would be sweet. Would there be more sugar in it? Yes. So if I was making maybe a teacup with sweet water and a big stock pot with sweet water, the stock pot has more water in it, right? If I put a teaspoon of sugar in the teacup and stir it up and taste it, it's like, yeah, that's nice and sweet. If I put a teaspoon of water in the big stock pot, is that going to taste sweet? No, I might not even really be able to taste it. In order to have the same amount of sweetness, I'm going to probably have to put a couple cups of sugar in there. Does that make sense? So the concentration is describing how much is in a given volume. And this 1.55, where is it? 1.55 liters is saying, this is how much of it I have. So I'm saying I have a cup of that water. How much sugar is in it? So this is the quantity, and this is the concentration. Okay? That's an excellent question. Any other questions? So, like I've mentioned before, putting this path together is the critical step in solving most of these problems. Once you get the path, there's a set pattern we can follow. Okay? So we get the path, and that tells me how to put this equation together. So I've got 1.55 liters, and I've got 2 arrows in my path. That means I've got 2 fractions. So this is going, come on, pointer. There it is. Liters to moles to grams. That's what goes here. Liters to moles to grams. That's where the path comes in. The path tells me what my path should be. Where do I go from here? How do I get from one place to another? And then I want my units to work out. So I want liters to go away, so I'm dividing by liters down here. So liters divided by liters cancel out. And moles divided by moles cancel out. The units are like variables in algebra, x's and a's and b's. They can cancel out. They can get squared or cubed. They can sit around and just be there. So we put the units in, and then we put in the numbers. So this concentration I was given, this molarity, relates moles of the sugar to liters of solution. So here where I have moles and liters, that's where I'm going to use this number. It's this many moles, and so that number has to stay with moles, 0.758 moles per liter of solution. And I could say per 1 liter if I would like, if I want a number down there. I don't have 1 liter, I have 1.55 liters. And then this last term is grams per mole, and that number's not given in the problem. But we have the chemical formula, and so we can calculate it using the periodic table. So there's 12 carbons times the mass of carbon, and 22 hydrogens, and 11 oxygens. So my calculator is telling me 342.296. It's really got 4 significant figures, but those 2 extras are fine. I'm just going to leave them there. So sucrose weighs 2.296 grams. 342.296 grams for every 1 mole. So now I can see I need to take 1.55 times 0.758 times 342.296 equals my starting number had 3 significant figures. My molarity had 3 significant figures. My molar mass had 4. So this is going to have, my answer has 3 significant figures. And so 402 grams of sucrose. If I had twice as much, what would that be, 3.10 liters? Then I'd have twice as much sugar. If I had half as much, I'd have half as much sugar. Any questions? Can you see why dimensional analysis is helpful in this class? I mean, just almost everything we do is using dimensional analysis. And I know that some of you are still quite iffy on that. And I think if you're willing to talk to me later this morning in lab, I think we can turn the corner and make sense of it for you. And then a problem like this is easy. Borrow 2 grams. Here's a conceptual connection. If we dissolve 25 grams of salt in 251 grams of water, what is the mass of the resulting solution? Do not overthink this. 25 grams of salt and 251 grams of water, what's the mass? I just add them, right? I just add them. 25 grams plus 251 grams. So what, 276 grams? So that's B. Does that tell me anything about the concentration? Well, I could figure out the molarity possibly from this, but it's not what it's asking about. So solutions are often stored as concentrated stock solutions. These are solutions that we keep in stock in the stock room. And then when we need something that's less concentrated, we dilute them. So it's a little bit like having the frozen concentrated orange juice in your freezer. And when you need some orange juice for breakfast, you get out the concentrate and you dilute it. To dilute something, you just add more solvent. The amount of solute doesn't change when you do this. Imagine taking the orange juice concentrate and pouring it into a pitcher. You've got a certain amount of orange goodness in there, right? If I add water to the pitcher, does it change the amount of orange goodness in the pitcher? It does not. It changes the volume because I've added water. It's going to change the taste of it. It's going to go from way too sweet to tasting good. But the amount of orange stuff is the same. So when we dilute a solution, the amount of solute stays the same. If we take the molarity of one solution times the volume of that solution, let's look at how the units would work out. The molarity of this solution, moles per liter, times the volume in liters, the liters will cancel out, and that'll give us moles. That would give us moles of solute in the first solution. When we dilute that, the molarity changes, the volume changes, the molarity goes down, the volume goes up, the number of moles stays the same. And so this is the equation we use for doing dilution calculations. M1V1 equals M2V2. So here's an example of diluting a solution. So we're going to make 3 liters of 0.5 moles per liter using a 10 mole per liter solution. So this is more concentrated. So we're going to take a little bit of the concentrated solution and add more water to it and dilute it. Just like you take the orange juice concentrate and add water to it and make it the right concentration. So I'm just going to write this on the side because that's kind of small down there. The idea here is that the molarity of the one solution times its volume is equal to the molarity of the second solution times its volume. So we're not doing the calculations here, we're just being told this is what was calculated. I'm measuring out 1.5 liters of 10 molar stock solution. So that's 10 moles per liter, because that's what the capital M means, times 0.150 liters. The liters cancel out, and that gives me, 1.5 moles? Yes. And over here, I'm going to end up with 3 liters of 0.5 molar solution. We're calling that solution 2. So the molarity of solution 2 is 0.500 moles per liter. And, well, let's be consistent here. We've got 3 liters of that. So the liters cancel. 0.5 times 3 is 1.50 moles. I put some solute in there. It was dissolved in some water. When I add more water, the amount of solute stays the same. The concentration changes, the volume changes, but the amount of solute stays the same. So we should be able to do problems like this. To what volume in milliliters should you dilute 100 milliliters of a 5.00 molar calcium chloride solution to obtain a 0.750 molar calcium chloride solution? Yeah, I can go back. So again, we've got a bunch of numbers here. Let's pull them out. Yeah, that didn't work very well, did it? I've got 100.0 milliliters of this calcium chloride solution. And I've got a concentration of 5.00 capital M, 5.00 molar. That's 5.00 moles of calcium chloride per liter of solution. And then it gives me another molarity, 0.750 moles of calcium chloride per liter of solution. I took the capital M's and wrote them as moles per liter because it's more useful. Like, okay, look at all of those numbers. What am I trying to find? I'm trying to find a volume in milliliters. Oftentimes, these problems actually have the word dilute in them, and that is your clue that you can do this with the dilution equation, M1V1 equals M2V2. Now, could you do this using dimensional analysis? Yes, you could. But this is a situation where most students find it easier to use the equation. So let's identify what these different things are. So 100 milliliters is a volume, right? So that's a volume. This is a molarity, and this is a molarity. Everybody okay with that? The ones and twos, which solution I call 1 and which solution I call 2 doesn't matter. It's not concentrated and dilute, it's just 1 and 2. I just need to get the volume matched up with the correct molarity. So this 100 milliliters, does it go with 5 or 0.75? Goes with 5. 10 milliliters of 5. Those two go together. I'm going to call them both 1 because they were first in the problem. So this is V1 and this is M1 because they're together. And so this other molarity is going to be the other one. It's going to be M2. And then what I'm finding is a volume, and that's going to be V2. So I take my equation up here, and I'm going to solve for V2. Algebra coming up. If I want V2 by itself, I can divide this side by M2, and it'll cancel out, leaving me V2. In order for this to be equal, though, I have to do the same thing to both sides. So I have to divide this side by M2 as well. So I rearrange the equation, and I get that the volume of solution 2 is equal to the molarity of solution 1 times the volume of solution 1 divided by the molarity of solution 2. Everybody okay with that? So I've identified what these things are. I'm going to plug them in, and I'm going to include all the units because that's what we do. So molarity 1 is 5.00 moles per liter. And volume 1 is 100 milliliters. And we might anticipate that there could be a problem with units, but let's just put all of it together, and oftentimes it'll take care of itself. So down in the bottom, I have the molarity of the second solution, which is 0.750 moles per liter. Now, what I've got for units is compound fractions. I've got moles per liter in the numerator and moles per liter in the denominator, and so they cancel each other out. Yes?
Would we ever have a problem where the units don't cancel out?
There are times where the units don't cancel out, and you'll have to convert milliliters to liters or something. Mm-hmm.
Is that if we're given like molarity as moles per milliliter or something? Like,
You'll
how
never
would
be
that-
given it as moles per milliliter.
Then what would be like an example?
So if it was asking me for the volume in liters, then I'm going to have to convert somewhere, because this is going to give me the volume in milliliters. This happens to be what I need, so we're going to leave it alone. So moles per liter cancel with moles per liter. If the units don't cancel out, then I need to do something with it. So I've got 5 times 100 divided by 0.75. And this gives me a really long number. V2 is 666.6, repeating forever, milliliters. How many significant figures should that number have? 3. This volume is 4 sig figs, but this concentration is 3, and this concentration is 3. And so this should have 3 significant figures, and so I'm going to say that this is 667 milliliters.
So we don't convert it to liters?
I'm not going to convert it to liters because it specifically asked for milliliters. Yeah. Sometimes it just says what volume, and then, I mean, you could convert it to gallons if you wanted to, and technically it'd be correct. But if it asks for milliliters, you better give it in milliliters. And then for dilution, we should always ask ourselves, does this make sense? So we're taking 100 milliliters of the concentrated solution, and we're diluting it, meaning we're adding water to it and getting a lower concentration. Should the final volume be larger or smaller? It should be larger because I'm adding water to it. It should be getting bigger. And so this volume is larger than the starting volume, and so that's encouraging. It doesn't prove anything, but it's encouraging. If I end up with that being smaller, I've got something backwards, and I need to go back and fix stuff. Any questions? 667.